I'm Terry Klinker. We're going to continue our discussion of sensitivity analysis. We're going to talk about how sensitive our solution is to the few changes in the objective function coefficients right now. Now let's go back and look at our problem. Remember our problem, we're trying to figure out what the proper mixture of tables and chairs is for our operation. We know that we make $7 for every table, x1 is number of tables, $5 for every chair, x2 is number of chairs. We went through and solved it. We found out that our optimal solution was going to be $4,040 was the most we could make, and we made that if we made 320 tables, 360 chairs. Let's go back to our graph for a minute. We know that our solution will be at one of the corner points that defines our feasible region. Now, why will it be the corner point? Well, remember, the corner points are where two constraints come together, where I have maximized two of my constraints, or at least two. The more of your constraints you use, remember, the more resources you have, the more money you can make. Well, the more of your constraints that you use, the more of your resources that you use, the more money you'll make. So you're going to make the most money where you have maxed out at least two of your constraints. In this case, then, our solution will be to make nothing, to make 500 tables, no chairs, no tables, 600 chairs, or the current mixture is 320, 360. These assumptions, $7 per table and $5 per chair, are based on market conditions. All right? So remember, market conditions change. We have no control over it. As I mentioned in the last video, we control carpentry and paint. We can control all of that. So we're going to focus on changes in the objective function. And what we call these numbers in front of our decision variables, we call them coefficients. $7 per table is the coefficient. For every table, I make $7 profit. For every chair, I make $5 profit. So how far can these change before we would want to make a different mixture? How far can the market conditions change before we would make one of these other mixtures? All right? So let's go through and take a look at it. What if, instead of $7 per table, I made $1,000 per table? All right, so it would be 1,000 x1 plus 5 x2, $1,000 per table plus $5 per chair. Well, in that case, I would probably want to make all tables and no chairs. Makes sense. If I made $1 per table and $5 per chair, I would probably want to make no tables and all chairs. Since this is my current solution, I want to find out how far these coefficients change before I prefer one of the other solutions. In other words, somewhere between $7 per table and $1,000 per table, because if I go to $1,000 per table, I would want to make all tables, no chairs. Somewhere between 7 and 1,000 is an indifference point. That's something we covered in an earlier chapter, in an earlier video. So we go up here and we want to find out what's the indifference point between what's the indifference point where I have the same value here as I do here? So what we have to do is we say, when is my indifference point, of course, is going to be when profit at my current objective function, or my current optimal solution, equals the profit at one of my adjacent points. So if this is my current optimal solution, the adjacent points are going to be the 2 points, the 2 corner points that are adjacent to that solution. Now I'm going to pick one or the other. If this is going up, if my profit margin for tables is going up, then I'm going to want to make more tables. Well, which one of these adjacent points is where I have more tables? Which one of these adjacent points is where I have more tables? It's going to be in a positive x1 direction. Here's my current optimal solution. Here are my two adjacent points. Which one is in a positive x1 direction from the current optimal solution? In other words, positive x1 is more tables. Well, this one goes backwards. This one goes forward. So this would be the adjacent point I'd want to use. So I'll have profit at the current optimal solution, which is 320, 360, is going to equal profit at the adjacent point, 500, 0. Now remember, my profit equals $7 per table plus $5 per chair. But what's changing in this equation? If it doesn't change from this, we know that this is the optimal solution. We know that we're going to make 320 tables, 360 chairs. What is changing in this? Well, the only thing that changes is profit margin on tables. You can't change two things at once. We have to hold one constant, all right? So that's the first thing when we're doing sensitivity analysis. So this is going to change. This is going to change to what? Well, it's going to change to 7 plus some unknown quantity, Q. I don't know what Q is. That's what I'm trying to find out. How far does it change before these two profits have an indifference point, before the two profits are the same? So this now changes to 7 plus Q times x1 plus 5x2. My new profit margin is 7 plus Q times the number of tables plus $5 times the number of chairs. So let's go over here and try this again. So this becomes 7 plus Q x1 plus 5x2 at 320, 360. And at the indifference point, that's going to equal 7 plus Q, again that change in the coefficient, change in the profit margin, x1 plus 5x2. At the adjacent point, 500, 0. Well, now all we have to do is solve for things. We stick this number in for x1, this number in for x2, this number in for x1, this number in for x2, and we solve for q. All right, we can do that. That's fairly simple. 7 plus q times 320 plus 5 times 360 is going to equal 7 plus q times that 500 tables plus $5 times no chairs. Go through and do the math here. We end up with 2140 plus 320q plus 1800. This is 2240. Sorry about that. Equals 3500 plus 500q plus 0. Again, go through and do some algebra. 320q plus 4040 equals 500q plus 3500. 180q equals 1040. No. 4040 minus 3500 is going to be 540. Q equals 3. The change, Q, all right, Q is $3. What does this mean? Well, it means that if my profit margin for chairs goes from 7 to 7 plus Q, 7 to 7 plus Q means 7 plus 3. So if it goes up to $10, I have an indifference point. The profit here equals the profit here. Let's stick it in there and find out. All right, so we'll make this the objective, the new and improved objective function is going to be $10 per table plus $5 per chair. Let's stick that in. 10 times 0 plus 5 times 0 is still 0. 10 times 500 plus 5 times 0 equals 5,000. So we would make $5,000 there. 10 times 0 plus 5 times 600 is going to be 3,000, so no change there. 10 times 320 is 3,200 plus 5 times 360, which is 1,800. So this is going to be 3,200 plus 1,800, and that adds up to $5,000. Now you can see we would make 5,000 here, 5,000 here. We now have multiple optimal solutions. We have an indifference point here. What good is that? Well, we know that if profit margin for tables is $10, we can choose either of these mixtures. On the other hand, if it's $9.99, if it only goes up $2.99, 7 plus 2.99 is 9.99, it would still be higher profit for us to make 320, 360. If the profit goes to $10 and a penny, we would make more money by making all tables, 500 tables, and no chairs. We could go back and do the other thing. We could go the other way. We could say, all right, what if instead of the price of, or the profit margin on tables going up, it's going down? We could find out how far it could go down before we have an indifference point. We could find out how far this one goes up or down. We could do it the same way. Now, I could go through that on the video, but it just takes practice, and I have notes out there to show you how to do that. In the next session, we're going to find out about shadow price.